All right, on tonight's episode of Python Papi, we're back inside our artificial intelligence course, and we're still doing our learning module. Let's have a look at what we went over tonight. Now, tonight we did have to start a new learning module. The last one got kind of long, so I did start a fresh one. So let's pick up where we left off. Yesterday we were discussing the L1 function, and tonight we're going to pick up where we left off from that. So L1 doesn't just look at if actual and predicted are equal to each other, but we take the absolute value of the actual value minus the predicted value. As you can see, that's the function here. That'll be this: actual predicted equals actual minus predicted. In other words, we just ask how far apart were the actual and predicted values, and we sum that up across all the data points to be able to get what our answer ultimately is. So what might this actually look like for our data set? Well, if we go back to this representation where we had advertising along the x-axis and sales along the y-axis, our line was our prediction or our estimate for any given amount of advertising, what we predicted sales were going to be. So let's have a look at it here. So you can see this is our sales axis and our advertising axis, and this is the line that tells us exactly what's what. According to advertising money spent, what was the revenue or the sales generated for the company. And our L1 loss is just how far apart vertically along the sales axis our prediction was from each of the data points, as I just explained. So we can figure out exactly how far apart our prediction was for each of the data points and figure out as a result of that what our loss is overall for this particular hypothesis, just by adding up all of these various individual losses for each of these data points. And we did that here. You can see we actually charted some lines here to see exactly how far away each of these cells data points were from the actual advertising dollar spent data points. So that's what that chart represents here. And our goal then is to try and minimize that loss, to try and come up with some line that minimizes what the utility loss is by judging how far away our estimate amount of cells are from the actual amount of cells. And it turns out that there are other loss functions as well. One that's quite popular is the L2 loss function. And the L2 loss function is just about the same as the L1 loss function. The only difference is that we're going to square the actual minus predicted outcome. So the L2 loss, instead of just using the absolute value, like how far apart away the actual value is from the predicted value, it uses the square of the actual minus the predicted. Square of the actual minus the predicted. So like I said, that's this here. So instead of just using the actual minus the predicted, we're going to actually use the square of the actual minus predicted. So how far apart are the actual and predicted value, and it squares that value, effectively penalizing much more harshly anything that is in a worse prediction. So because it's getting squared, the penalization is going to be a lot higher than just the actual takeaway predicted, because we're squaring it, so it's going to come back with a greater number. So imagine that we have two data points that we predict as being one value away from the actual value, as opposed to one data point that we predict as being two away from the actual value. The L2 loss function will more harshly penalize that one that is two away, because it's going to square however much the difference is between the actual value and predicted value, as I just stated earlier. And depending on the situation, we might want to choose the loss function we use, depending on what we care about minimizing. Now that's where I'm going to stop tonight. We did take a lot more notes, but I'm not going to dive into everything. But again, we will pick it up tomorrow, and I will keep you guys posted every step of the way. But for now, this is the Python Poppy. You guys stay Gucci.